Before I introduce my project, I'd like to briefly explain the motivation behind it. In our current electrical safety testing room, we use a commercial system called the ThermoLogger. It's an accurate and reliable piece of kit for temperature measurements. However, it has several practical limitations in our environment. Firstly, it's quite bulky and it's not easily portable between different tests. Secondly, it depends heavily on an external PC to operate. This makes it less flexible for field or standalone use. Additionally, the ThermoLogger doesn't include any built-in safety features, such as automatically isolating the system under test if it was to reach a critical temperature. And finally, for basic logging needs, it's a relatively high cost solution. These currently retail at around £600 from RS Components. So recognising these gaps, I decided to develop a system that would be more portable, self-contained and safety focused, while still achieving the same accuracy as the ThermoLogger. So that is my project motivation. Having established a motivation around this project, now it comes to the project objectives. So the project objectives are to design and build a 4-channel temperature logging system using K-type thermocouples. The captured temperature is then to be displayed on a TFT LCD screen. I chose 4 channels as the system we use at the moment. We never use any more than 4 channels, so it only makes sense to make a 4-channel temperature logger. For safety, the system is to include features such as a relay cut-off in the event of a thermal failure. This would basically cut off the system under test if it was to reach a critical temperature. And also we're to provide time-stamped data logging to an SD card in CSV format. This could then be removed and plugged into a PC and then used for reporting. We're going to need a user interface where we can select the safety cut-off temperatures as well as the sample times, and also whether or not we want to log or not. And finally, we're to achieve a comparable accuracy to the ThermoLogger, and those are the project objectives. So this slide shows the system block diagram of the final design. I decided to use the ESP32 MCU for future scalability, such as Bluetooth or Wi-Fi. You know, in the future you might want to be able to view it on your phone, for instance, or a web page or some sort. So if we go down to the bottom there at the analog front end, you can see the 4 K-type thermocouples. Each are filtered by a first order RC low pass filter. These will be in differential and common mode for filtering noises such as mains or any switching noises from switch mode power supplies, and atmospheric noise also. I thought this was important because if we want to achieve the same level of noise as what the Pico gives us, we're going to need very good filtering. So from here it goes into a multiplexer, which then outputs to a differential amplifier. This is a very low noise instrumentation amplifier, because you've got to remember that the K-type thermocouple only gives out like 41 microvolts per degree C. So from here I scaled that up to 5 millivolts per degree C, going into the 16-bit ADC. And there on the left there we have the LM35, which is taking care of the cold junction. So these 2 signals will basically be sent on the I2C port, where they'll be processed in the ESP32, such as cold junction compensation. So if we look at the SPI port, we got the LCD and we also got SD login. We got general purpose I/O for the button interface and the important relay, and not forgetting the RTC for the timestamps, and that too will be sharing the I2C port. And basically that is the high level system block diagram of my design. So here's the finished system. So there you can see the sample time on the left and the max temperature set time on the right, the logging switch in the middle and reset at the top. There's a close-up view of the relay circuit. You can see I've put some slots in the PCB there for creepage reasons and high voltage to DC circuits. See RTC. There's a close-up of the relay connector and the safety fuse in. There's the filter circuit and the LM35 cold junction compensation, all the other circuits there. Got the op amp, the multiplexer. Now we're going to boot up. So there's the boot up screen. I thought I'd design a nice boot up screen. Thought it'd be a nice touch. And there's channel selection, so you're not always going to be using 4 channels, so you can select whichever ones you want on, and you monitor that channel. So as we're using 4 here, we'll switch them all on. So there you go. Yeah, so for the system I introduced like an engineering mode, it's like a calibration mode that you can enter by pressing two of the buttons on the user interface, and that's the max temp buttons here, which is just going to show that. So basically that is the output scale factor of the operational amplifier, and you can change this from here, which gives you the ability to calibrate the system to any other system or other temperature standard. So that has been calibrated to the values I use throughout this project. There are the 4 channels again. So we select all 4 of them. So there, so if you look at the top, we've got the time and date, and down the bottom we've got the sample time, which I think I changed now. Just bring that down to 1 second, and also set max temperature. I want to bring that down to 30 degrees because I want to demonstrate how the relay works. So I'm going to touch one of the channels to activate the relay. So that's what I'm doing now. I'm just setting that to 30 degrees, I believe. There you go. So what we do now, we'll start system login. So we'll do the center switch to the right to put it in login mode. And as you look down the bottom now, you should see that we're actually logging, and it will tell on the LCD how long you've been logging in minutes, which I think is quite a useful feature. So we go on, just about touch channel 1, I believe. Yes, there you go. And that's the relay activating. That gives you a warning sign on the LCD. So the relay will only disengage if the system is reset, and that is a safety feature because you don't really want the system keep being switched on and off while the temperature lowers. So what I'm going to do now is remove the SD card and plug it into a PC, and we can view our logs. So here we go. There's a SD card adapter there. And there you go. You can see 2 files there. So you've got the log switch, which we're going to open now. Basically, this will tell you the time and date to a second when and at what temperature the relay activated. So that'll be a good feature for reporting. And here's the CSV log file. And also this log file will tell you the time and date and the sample time that it's logging in. This will be a useful feature if let's say that a temperature event happened at a certain area, you'd know exactly what time to the second that occurred. And there you go, we're just show the chart now, recommended charts. And there you go, you can see channel 1 there is activate the relay, and all the other 4 channels, 3 channels are ambient. So that is the demonstration of the ThermoLogger. So to get an accuracy metric of my design compared to the PicoLogger, I used a climatic chamber set at different temperatures over time and compared both systems that way. As you can see in the image there, we've got my design on the left, the PicoLogger on the right, and we have the climatic chamber in the centre. So this slide shows us the results accuracy when compared to the PicoLogger. As you can see, the results were gathered from 0 to 100 degrees C in 10-minute steps. So if you look at the typical accuracy of my system when compared to the PicoLogger, you're looking at plus minus 0.3 of a degree C, or a typical worst case at higher temperatures at plus minus 0.7 degrees C. So I'm really pleased with these results, because these results prove to me that my system is comparable to the PicoLogger when it comes to temperature accuracy. So this slide shows the noise performance of my system when compared to the PicoLogger. So having already collected the data from the accuracy that I'd done previously, I used that and took the standard deviation of both systems' range and peak-to-peak noise. And as you can see there, my system, the ThermoLogger, is slightly less noisier over that temperature range than the PicoLogger. So I use this data in MATLAB and did an FFT noise performance on both systems. And as you can see there, the PicoLogger is suffering from some noise at the 0.3 Hz range, and my system doesn't. So really pleased with these results. So in conclusion, I'm really happy with this design. It's a functional and accurate 4-channel temperature monitoring system. It offers real-time display, reliable relay cut-off protection, and also includes SD card time-stamped data login for reporting. So future improvements. As the system's core is the ESP32, this comes as Wi-Fi and Bluetooth ready. So I could add cloud connectivity, or even build a mobile application to view the temperatures, or even control the system from a mobile phone. The design was designed to be integrated into a case. However, due to time constraints, this unfortunately could not be completed in time. However, this is being undertaken by mechanical engineers at present as we speak. So yeah, I can't think of any more improvements as it is, but thank you very much for watching.